First, let's investigate the two-step elimination reaction. Here's the overall elimination reaction. Recall that it's the halogen and the proton at the beta position that are being eliminated, so this is called a dehydrohalogenation reaction, and that's an example of a beta elimination reaction. The product of the reaction, the major organic product is going to be this alkene product. That's what we're interested in. You have an inorganic halide that's formed, and then you have this protonated base as the byproducts. We want to first look at this two-step process, and so the first step of this reaction mechanism should look very familiar to you because this is actually the same as the SN1 reaction first step. So it's carbocation formation. The second step's a little different. This is where you have a base come in and deprotonate at the beta position, and then the pi bond is formed from these two sigma electrons that are left behind. If you were to take a look at an energy profile of this reaction, you would see that, of course, it is two steps as shown here, and it's the first step that's the rate determining step. In fact, this looks pretty much exactly like the SN1 energy diagram. You have the transition states, of course, at the top of the hills here. The intermediate that we are talking about, again, is a carbocation. And so what we're interested in are factors that can stabilize the transition state and therefore lower the activation energy barrier of the slow step, which is the first step. And so we're back to factors that stabilize a carbocation. So just to reiterate, it's the carbocation formation, this first step, that's the slow step of this reaction. And if you were to take a look at the rate law, you would see that it looks exactly the same as the SN1 rate law. Remember that there is an exponent of 1 that's not shown here. So this is exhibiting unimolecular kinetics as well, but this time it's an elimination, and so we call this the E1 mechanism. The good news is that the same factors that favor SN1 also favor E1 because they have the same rate determining step. So if you recall, with an SN1 reaction, the ideal substrate is a tertiary substrate because of the carbocation stability. It will also work with secondary substrates. However, the primaries and the methyls will not undergo E1 reactions, just like they will not do SN1 reactions. The carbocation is just too unstable. In terms of leaving group ability, it's the same rule. The leaving group, the better leaving group is always the weaker base. And so the series will follow the same trend where I- is the best leaving group and F- is the worst leaving group. As far as solvents go, just like SN1, E1 is favored by polar protic solvents that can solvate the carbocation as well as the leaving group very well. And bases, typically weaker bases are used for E1 reactions since the base is not in the rate determining step. Recall that the E1 reaction is going to give an alkene product. And this alkene product can be a mixture of stereoisomers. So for example, if you were to run an E1 reaction on this tertiary substrate here and eliminate the halogen as well as the beta proton, there are two possible ways you could draw the alkene product. You could draw the product with the ethyl and the methyl group on the same side, and that would put the hydrogen and the methyl group on the other side. Or you could draw the product with the methyl groups both on the same side and the ethyl and the proton on the same side here. And what we're going to find is the major product in the reaction is going to be the one where the steric interactions are minimized. So for example, it's going to be less favorable to have an ethyl and a methyl group essentially eclipsing one another than it would be to have two methyl groups eclipsing one another. And so while these are not exactly cis and trans isomers, we will get to the naming of these types of isomers in a later chapter, they are two geometrical isomers. And the major product in the reaction is going to be the one that's shown here. We would say that the other product that puts the methyl and the ethyl group across from one another, you might still get some of this product, but it would be the minor product in the reaction.